Take a look at these corrugated steel silos stretching to the horizon. They represent the sheer scale of global agriculture, but their primary job is highly specific, preventing the crop inside from rotting. Freshly harvested grain holds natural water, and in a confined space, that moisture acts as a biological catalyst. If left unchecked, it triggers mold growth and spoilage, leading to total harvest loss. The standard solution to this biological risk is aggressive dehydration. Industrial dryers pull moisture out of the kernels, creating a stable environment where the crop can sit in a bin for months or years. But grain is rarely meant to stay in a silo. To become useful as animal feed, it eventually leaves the stable environment and enters a processing facility, defined by intense mechanical stress. This creates an engineering paradox. The exact physical properties that preserve the grain in a silo create a specific set of mechanical failures once it enters the high-pressure environment of the mill. Inside the processing facility, the grain is routed through a series of belts and pulleys into a machine known as a roller mill. The engineering intent of a roller mill is specific. It uses heavy steel cylinders to apply pressure, designed to crack a kernel open cleanly so the nutrients inside become undustable. It is not intended to grind the grain into flour. This is where overdrying becomes a liability. Inside the kernel, water acts as an internal structural binder. When too much moisture is removed, the kernel loses its natural elasticity and becomes brittle. When a brittle, dehydrated grain kernel is pulled into the narrow gap between these heavy rollers, it cannot withstand the pressure. This side-by-side comparison shows the material failure. On the left, a hydrated kernel splits neatly. On the right, the dry kernel shatters. Lacking internal moisture, the grain produces unpredictable shards, generating unwanted microscopic fines that trigger mechanical problems throughout the facility. To see the impact of those shattered particles, we must look at the facility's scale. Processed grain travels through a network of tall vertical drops, long chutes, and fast-moving conveyors. Because the kernel shattered instead of cracking, the resulting flour and fines easily go airborne during transport, creating a heavy influx of dust. That airborne dust acts like an abrasive, wearing down corrugated rolls, eating through steel bearings, and degrading internal mechanics. Inside the enclosed spaces of the elevator legs and storage bins, this dust concentration continues to build, swirling in the trapped air. When suspended in an enclosed space, high concentrations of grain dust are combustible. A single spark from a worn bearing can ignite the particles, leading to a dust explosion capable of destroying a concrete tower. Excessive dryness naturally creates a dangerous trade-off. While the grain is safe from mold in the silo, the resulting dust degrades the facility's machinery and increases the risk of a catastrophic event. Even if the machinery survives the abrasive dust, the consequences of over-dried grain follow the product to its final destination, the livestock feed. Modern feed mills produce a total mixed ration, or TMR. This is a calculated blend of grains, proteins, and vitamins. Keeping these ingredients uniformly mixed requires exact, consistent particle sizes. Irregular fragments ruin this uniformity. While properly cracked pieces lock together, the small shards and flour sift through gaps. During transport, constant vibrations shake the ingredients apart. Heavy pieces rise while nutrient-dense fines fall to the bottom, destroying the ration's nutritional consistency. Because the grain shattered in the mill, the livestock at the trough receive an unpredictable diet, which can negatively impact their intake and growth. To prevent these issues, modern feed mills use active moisture management rather than processing grains straight out of storage. Quality control begins with inspection. Technicians take moisture measurements from incoming deliveries, establishing a baseline for the physical state of the crop. If the grain is too brittle, mills use a process called tempering. They reintroduce precise amounts of water back into the dry grain inside a controlled mixer. By allowing the kernels to absorb this water, tempering restores the grain's structural elasticity. This ensures that when the grain reaches the rollers, it cracks instead of shattering. This requires a continuous feedback loop. Operators constantly adjust roller settings, measure moisture, and check particle size to maintain a consistent output. The goal isn't the driest grain possible, but the specific moisture level required for the task. Managing the balance between preservation in the silo and the physics of the roller mill allows a facility to operate safely and efficiently.